Everyone, it's my pleasure to announce the 4th workshop on proximity perception in robotics. This year's topic is on increasing safety for human-robot interaction using tactile and proximity perception. I would give you a brief outline and general information about this year's workshop, how we organized the workshop, and what is the plan of the workshop. First, I would like to introduce our organization team. I will give you a short introduction to the workshop, and I will also briefly explain to you how we structure the workshop this year. This year's organizing team is like a broad organizing team all across Europe. With different universities involved. So we have Kasper Althofer from the Queen Mary University of London, with Vana Boobetsu from Joanneum Research, Itao Ding from the Technical University of Chemnitz. We also have Stefan Navarro from INRIA in France, Lisa Marie Faller from the FH Kärnten, Jan Steckel from the University of Antwerp, Ulrike Thomas from the Technical University of Chemnitz, Björn Hein from the Hochschule Karlsruhe, and Hossam Alagi from the Karlsruhe Institute of Technology, and myself, Christian Schöffner from the University of Klagenfurt. The topics of interest. So the proximity perception workshop is now in its 4th edition, and our focus was always mainly on proximity sensing and also multimodal sensors, which is now getting more and more attractive in this domain, like tactile sensors and shear sensors. But we are also interested in robotic skins and the architectures involved for developing these robotic skins. And our main focus and goal is to bridge the gap between proximity perception and tactile perception, as we think and we believe that these two fields are getting more and more important in the future, and also applications involved. So for example, we will have human-robot interaction, human-robot collaboration with AI-based technology, and we really believe that bridging the gap between these sensing domains will enhance this further for future robotic systems. What are the goals of our workshop? So we have industrial partners who will give talks, and we will also have scientific partners who will give talks. And we want to continue to foster this community of roboticists and hardware developers working in these domains of proximity and the tactile sensing domain. We also want to provide insights in current research in industry on safety-related applications, as we think that safety, especially for the application of these robotic devices, is very important. And we want to let experts in multimodal perception and human-robot interaction give an account of their experience. And what's also very important to us is how we want to continue to bridge from science to industry. And also, what we also feature this year, again as last year, we offer PhD students a platform to present their research to a wider audience. And we think that this is quite a unique feature, that also young PhD fellows get the chance to present their work to a broader audience and also to other professors and people from industry. And we want to promote the scientific collaborations between the participants of the workshop. And now we'll give over to my colleague, Itao Ding, who will continue.
So just a few further information. So if you want to stay in touch with us, we have a mailing list where you can subscribe. We have here the QR code. And if you want to have further information, you will receive some emails. There are not very many emails, but if we want to announce something, we usually use this mailing list. And also, if you want to support us, in the organization team, you can provide some ideas for future events, or if you want to participate with the organization team, you can join us. Just contact us, and we will include you in the next organization team. And as for the structure of the workshop, we have an IROS-like event, which is 2 hours, where we have the panel discussion. So every speaker and every invited speaker and all the students in the PhD forum will participate in this panel discussion, where we discuss about different topics, especially for the connection between industry and research this time. And right now we are recording the on-demand material, which will be submitted to the IROS system as video, which you can access anytime. So all the speakers, invited speakers, will participate in sessions, which we will record or pre-record and data upload. And as Christian already said, we have a PhD forum of around 3 to 4, well, I think this time it's 4 to 5 PhD students with talks about around 15 minutes. And there you can meet and chat with your research colleagues and discuss about your own research. I think that's quite interesting. And yeah, and now we will start with the actual session of this workshop. Today we have 2 talks. Yeah, where the talks are split in around 25 minutes talk and 5 minutes discussion. But if you like, we can further discuss after the 2 talks.
So I can start introducing Dr. Kirill Safronov. He's principal developer at KUKA, which is one of the most important robotic companies in the world. He's been working there for more than 7 years. Before that, he was at Vision Tools and at the Karlsruhe Institute of Technology, where he also got his PhD in 2009. I actually met Kirill when I was in Augsburg in Germany, and I had the opportunity to see his work, and I immediately thought of him for this workshop. I'm very happy that he agreed to present his work. I'm sure it will be very interesting. Yeah.
So Kirill, can you share your screen? And your audio is turned on.
Okay, can you see it?
Yes.
Yes.
Hear me?
Yes.
Okay, so hello and welcome to my talk. Today I would like to present you the application of machine learning based technologies for bin picking automation at KUKA. So shortly about corporate research. At corporate research at KUKA, developing new technologies and innovations for the, how we call it, fourth robotic revolution. So we would like to make robots more cognitive, sensitive, and safe. You can see here the overview. At KUKA, we think the 4 robotics revolutions, and we are now at the 4th step. For example, I can mention one project that we had in previous years. Hybrid, it's stands for hybrid and intelligent human-robot collaboration, and we developed a robot, dual-arm robot, based on the mobile platform to help humans to perform some task, which is maybe not so easy for a human. For example, to hold some heavy parts at car production, and the robot has a camera, can accept the environment, can detect the objects, can navigate through the environment. So it's our view on how it should look like in the future, how the production should look like in the future. But today I will talk about the bin picking projects at KUKA. Which projects do we have? About different techniques, for example, grasping using machine learning, from object localization to sampling. Also about path planning, how we can implement reactive online obstacle avoidance, also using radar and time-of-flight sensors.
Yes. Sorry, Kirill.
Yes.
I think we have some audio issues. Can you maybe speak a little bit closer to the microphone? I think your noise suppression algorithm always kicks in and reduces your volume.
Okay, now it's better?
Yeah, now it's better, yes.
Okay. So at KUKA, we have different bin picking projects, a lot of funded projects, for example, like Translearn, where we're trying to train our neural network in the simulation and then transfer to real world. We're dealing with non-objects of the future. It's our current project when we are trying to detect the similar but flexible objects for food production, for example, fishes. We use the 3 or 4 finger gripper, then item pick project. When we are dealing with an unknown objects, we pick these objects. So it should not be so precise. So we are using a suction gripper. And we have a lot of classic bin picking projects. When we have the CD model of the objects are known, and we try to precise grasp these objects using 2-finger parallel gripper. So I would like to introduce the Picker Feature project, which sensors we used to detect these deformable similar objects. We have 2 systems. We have the mobile system, which consists of the 2 cameras, the all but good isosection camera, then sensor camera. It's a 3D sensor, used structured light, and static camera system, which consists of the different cameras like Civet, 3D or Photoneer, which are very precise. And we're using robotic gripper. The pipeline looks like this. So we have 4 steps. We have, first of all, we have to detect the pose of the object using a machine learning based technique or CAD matching, the classic technique. If the objects are recognized, we try to calculate, try to detect the grasp, all possible grasps without considering the collisions with the object. Then we have a list of the grasps. We have to select which grasps are possible for us for our system. Here we are using deep learning, machine learning based system, and the last step is the path planning. So we're trying to calculate, to plan the path, the trajectory, which has no collision, and which we can, the pose which we can reach using this trajectory. So first about the object localization. So in this project, we are cooperating with our partners, which provided us a method based on CAD model matching. So we're trying to detect these fishes. The fishes are tummy fishes. It was not so easy to use the real fishes. We matched the generic model of the fish. In this case, it was a tuna fish. So you can see on the middle, picture in the middle, it works quite well, maybe a little bit shifted, but it's okay for the fishes to grasp them. If we want to detect the fishes more precisely, we had to generate 3D models with a mobile scanner. But it took too much time for this. So we decided to use the machine learning based technique to detect the objects. Also, if the fishes are not similar, they're always, they're deformable, they have different sizes, different colors and so on. So we decided to use the dense features using neural network. So we trained our system to calculate the descriptor map, the dense feature map from 2D color and depth image. So you can see here for 2 examples, 2 fishes which are different, it's the same, different color, different size, and 2 descriptor images. You can see that if we define 3 features, for example, we defined eye, center, and back fin, and we can find the same descriptors on the other images. The features are not the same, but the descriptors correspond quite well. Also, if the fish is deformable, it's not a problem. If the lighting conditions are not the same, it's also not a problem. Some results. We tried to detect the single fishes. We tried to detect the pile of objects, and we find out that if we detect the single objects, it works quite well. So we can find the features. For example, here you can see 3 heat maps, heat map of an eye, the probability that the feature is there, heat map of the center and the back fin. So actually it works quite well. Sometimes we have mismatch. If we have a pile of fishes, if the fishes are close to each other, some features are mismatched or misaligned. We decided to use the segmentation first. So we segment the fishes or objects, the topmost object first, and then we detect the features just in this crop from the image. There's a video of our results. You can see the segmentation, the segmented fish. You can see the features which were detected just on this fish, and this descriptive map, which actually is not so, looks not so nice if it's not segmented, but if it's segmented, we can detect the fishes and extract the fishes from the bin. Also, we got some examples of the real fishes, or pictures of the real fishes from our partners, and we used the train system, and we tried to recognize the features, and it worked quite well. So also, you see that the pictures are quite different from the train for the pictures which we used for training, and we can still find the same features. So now we have the poses of the objects, and we trying to calculate the grasps using simulation. And another point was to simulate also the grasp. So how good is the grasp? For example, if the grasp is not so good and the object could be lost, we remove this grasp. So we can do this in the physically based simulation. We can calculate all possible grasps. We can remove the grasps which are not so good. But then we have to select the grasps which are more stable. For example, we can use the angles of the gripper. We can use the openings within the fingers, so different data which we can gather without machine learning. And then we can train our system also in simulation and transfer this system to reality. So we find out that it can bring very much actually in the performance, and the graphs became more stable. So small short video about our results. Grasp calculation. So we have a CD model. We can also use a point cloud from the fish, for example, and we can calculate all possible grasps. Then we filter out these grasps, as I explained already in the previous step. We can prune all these grasps. We can do physics simulation, and if the object is lost, so we remove these grasps. After this, we can take a bin. We can simulate the pile of objects and try to detect these objects in the simulation. When it works quite well, if the system is ready, so we can transfer to the real system and grasp the real objects. This is a video of our prototype system using machine learning based detection and robotic gripper. So you can see that we can grasp fishes. We can detect the fishes, we can grasp the fishes, we can have collision-free movement of the robot. For sure, the grip is not so perfect for such an object. For example, some flexible gripper would be better. Also, another problem is after grasping, if the object is shifted. So we have to localize the object in the gripper to place it more precise. So we did it using visual sensors, but we were thinking about using some tactile sensors to detect the position of the fish in the gripper. It's just ongoing tasks, so it's in progress. So the project is still active. So the next step, it's a collision-free path planning. We use normal algorithm. So I have some problems with video. Oh no, okay. So we use CD model of the environment. We use a CD model of the objects in gripper to detect the collision, to calculate the collision-free path. Also, we can use the point cloud with dynamic data to detect this, to calculate the collision-free path. Therefore, we developed a system for calculating the shortest distance to the obstacles. If the obstacle is static, like for example, table or robot fixture, it's not a problem. If we know the angles and so on, we can detect the shortest distance to the obstacle. Like here, for example, we take the link of the robot and we, from each link, we try to calculate the distance, the shortest distance. If the distance is smaller than some threshold, we consider this position of the robot as in collision. It would be also nice to have to use this system in dynamic environment like this. So we have two robots. One robot is performing one task, for example, picking some objects from the box and transfer to other table. We did it using just the calculation, but not offline, online calculation. So we use the current position of both robots and we can calculate the distance. Looks like this. So the one robot, which is on the right, performs some tasks. The left robot has another task. It's has more priority. So if the right robot moves towards the second one, it can collide with the second one. If we switch the tasks and the task of the right robot gets more priority, the second robot moves back. So there's a simulation of our calculations, and actually it would be nice to calculate all this movement without using axis positions, but to use some sensor data. So our idea is to mount radar sensors on the links of the robot. For example, the small radar sensors, which can generate the distance, which can calculate the distance to the nearest object, and we can use these distances. So should look like this. We did it in simulation. So the radar sensor gives us just a distance to the next point, of the dynamic object, and we don't need information about the current position of the robots, so we can save some time and perform the task more quickly. About the radar sensors, we have another project, and in this project we developed a mobile system and we compare the LiDAR and with the radar sensors. For example, we mounted radar sensor on the mobile platform, and we try to detect the obstacles like this, the wall, the box, and another wall. And we find out that, for example, using LiDAR, we can get just a line. So we describe this wall using radar. We can get not just this wall in 3D, but also the box behind and another wall behind the box and the first wall. So it brings a lot for mobile manipulation. So we did other tests. For example, we tried to classify some objects and compare with the camera recognition. With camera, it's very easy. If you have 2D image or point cloud, we can detect some structures in the image or in the point cloud. The same we can do in radar's image. When we're using just a LiDAR sensor, we can get just the 2D points, and actually we don't know, we can distinguish between two these point clouds, 2D point clouds. If we use the camera or if we use the radar, we get the 3D point cloud, take some structures which are similar to each other, and classify these objects, so like a human or like a car. That was a one test, and another. What we tried to use the radar to detect some obstacles which are not so easy to detect using the camera. For example, the mirror or the transport object like a bus. So on this picture, you can see the map generated by LiDAR. On the right side, you can see the map which is generated by the radar sensor. If we take a look to this wall, for example, on the LiDAR map, it's just line. Here we have on the right side, we have a point cloud. So not just the wall, but also some parts of the table above the wall. So we can do some classification and we can detect the wall, we can detect the table. So the problem here, the box is standing behind the mirror, and LiDAR cannot detect this box. So the box is invisible for the LiDAR sensor. For the radar, it's not a problem. We can see through the mirror, we can see this box, we can put this box into the map and consider like an obstacle. Also, you can see that the mirror, it's present on the map, on the radar map, but it's doesn't present on the LiDAR map, and it's also negative. We have some points which are not there. So it's a problem of mirroring. Also, as I said, we can get more points, more data. For example, robots point cloud, and we can. So we try to implement this idea for navigation. So we put two objects, the mirror here and the glass, the transparent object, and try to navigate just with the radar sensor, using just a radar sensor. And you can see that the robot can move, can detect these two objects and can move through these objects without collisions. So the same idea we can use also for our bin picking system to detect other objects, so putting the radar on the links of the robot, as I told before. So it's a very promising technique, and it's we'll try to do this during this. What we did shortly about time-of-flight sensor for safety. Also, we have some project in safety. The advantage of the sensor, it's not just it's very fast and it has low noise, but also that we can identify people. It's very good for the data privacy and so on. So we have one project, a new project. It's called RoboMove 3D, where we're trying to use different sensors for safety and to compare the sensor, for example, time of flight or radar. And in conclusion, I could say that so the topic of this workshop is proximity sensors. So how we can use the proximity sensors in the industry. As we find out, the tactile sensors can be very useful for in-hand object localization, to localize the object when it's present. We are also trying to implement a system using radar sensors for online obstacle avoidance, for multi-robot systems. For mobile robotics, the radar sensors can be very, very useful. Also for planning, collision-free path planning in the map, and detecting difficult objects, and for safety. So thank you, and I also would like to thank my colleagues which worked on these projects.
Thank you very much, Kirill. That was really a lot of extremely nice examples. I would like to, yeah, exactly. So if there are any questions also from the audience, please just raise your hand, as some people already did. So I would go ahead. Mr. Pilz, you already have a question?
No, not a question, just the wrong click, but congratulations to the work shown in this research.
Yeah, so I would go ahead. Kaspar, you also have a question?
I think Matteo was before me.
Okay, yeah, I don't see the order, so go ahead, Matteo.
Really nice work. I was interested in knowing if, so you showed that from radar sensor, you build this kind of point cloud, and I was wondering if this going from the raw data from the radar sensor to point cloud is something that you developed in-house, or if it's something that is given by the producer of the radar sensor.
Yes, so we're using point cloud directly from, so we are getting point cloud directly from the sensor. So it's already provided by the manufacturer of the sensor.
Okay, thank you very much.
Yeah, also from me, I mean, fantastic presentation, and yeah, nice to see what's happening at KUKA. So yeah, thanks a lot for that. I liked your presentation, especially on the grasping side, and so I had the feeling you are focusing quite a lot on the image processing and the object location through vision. I'm wondering, where do you see the main challenges in grasping? Is it that what you were focusing on, or is there also a need to further develop grasping devices? And you mentioned in the last slide tactile sensing. Are these issues as well that need to be addressed?
Yes, so the main problems for industry, first of all, we try to make the commissioning of the system more easy. For example, we're trying to develop a system that's not hard coded. So we want to specify the grasps, not like before, using some graphical interface, but to calculate these grasps for precise grasping. Second problem is the collision-free grasping. So how we can detect the collisions fast, for example. And if we have two different systems, two robots, how we can make a system which doesn't collide. I mean, when the robot doesn't collide with other robot. And the third problem is this in-hand object pose localization. So it's very, very crucial for machine taming. So if the object is grasped, normally it's always a little bit shifted, or maybe during the movement it's shifted. So, but we have to put this object very precisely to the machine. And also another problem is grasp selection. So which grasps are very, very good, because sometimes the system can recognize the grasp, but if we try to grasp this object, it's not so good. So we can lose the object, or we can grasp not precisely.
Thank you. Maybe I can just ask again. So the grasping device that you're using, you're happy with, or could you also envisage that? Well, do you see a need for further development there, so that I mean, maybe I should say I'm very interested in soft robotics. So do you see a possible route in that direction to improve?
Yeah, for sure. The grippers which we use, they are more for industrial use. So for example, for our project, for Pico Future project, the system should work in the food production. And soft robotics gripper, for example, could be very useful there. So we plan also to test other grippers which can be also certified for the food production.
Okay, yeah, thanks a lot.
Thank you. So next one I have on my list is Stefan.
Oh, yeah, thanks, Kirill, and nice to see you again. Yeah, actually, my question was similar to Kaspar's, so that maybe asking about the potential you see in soft robotics grippers to deal with, pose uncertainty, and do you see? I mean, besides the aspect of being suitable for food handling, this idea of embedded intelligence. For instance, you mentioned, for instance, that you have pose uncertainty when you detect the fishes and so on. And do you see that the way of looking into embedded intelligence is going to solve or address these issues, or what is your take on this?
Yeah, for sure, it would be nice to have some system which can be possible to detect these offsets in the group and so on. For now, as I said already, we use the visual system to detect the object position in the gripper, but then we have to mount the camera somewhere. So we have also to deal with the different lighting conditions, and also think about the space and so on and so on. So it would be nice to have something in the gripper embedded to detect this pose of the grasped object directly.
Okay, thanks.
Thank you. Next one I have is Christian.
Yes, thank you, Kirill, for your talk. Really interesting research and work. I have two questions. So the first one, you showed really nice results using radar sensors for navigating this mobile platform. I'm just wondering, so how do you deal with multipath, or in general, is multipath an issue? Have you encountered this in your research, or is this still something you need to investigate?
Yeah, so we have to work on this point. So we started this project. We did some tests, but it's still a current active project. So we have a lot of problems which we have to solve.
Okay. And my second question is related to the grasping. So you showed that you successfully grasped these toy fishes out of the bins, right? I was just wondering, have you also tried this on real fish? Because I would assume the real fish is like wet, kind of slippy, and how does this affect the grasp performance?
Yes, it's true. So what we tried to detect the real fishes because it was easier. We could test on the fishes in the packages because it's not so easy to organize the testing system with real fishes in our lab. Therefore, the grasping we didn't test the grasping of the real fishes. We tested just the object recognition. Our partners, so these partners are in France. They developed the gripper especially for fishes, using the suction cups and so on. So they did some tests. Yes.
Okay. All right. Thanks much.
Thank you. Itao, go ahead.
Sorry, my audio was turned off. Yeah, thank you for a nice presentation, Kirill. I really like the results of your multi-robot platform. So I really was surprised. I have two questions. First of all, I saw that you have attached the sensors on, I think, at the end effector, I think, or close to the end effector. Do you also consider the redundancy of a robot? For example, if the sensor is attached on one of the lower limbs, does your reactive motion platform or framework also work in that regard?
Yeah, for vision, for object detection, we have two systems, so static system outside the robot kinematic and one mobile system, which is mounted on the end effector, but also we are planning to attach the radar sensors or maybe some small time-of-flight sensors on the links of the robot to detect the distances to avoid the collisions, but not for object recognition.
Okay. And I also, there's usually, I think, I'm doing a lot of research right now in terms of reactive motions. So in your dual platform, the motion was pretty smooth. So with reactive motions, you sometimes have the problem that if you, for example, trigger a motion, the motion gets a little bit jerky. I just wanted to know, do you have the same problems, or if yes, how did you solve them?
So yes, I think we had these problems, and we're also trying to solve these problems. So honestly, I'm not the expert in the motion control. So my colleague or my colleagues, they're working on this topic. So, but I know that there are some problems, and we're trying also to solve these problems.
Okay.
Thank you. Hubert?
Yes, thanks also from my side for the very, very nice presentation. One question regarding the radar sensor for the collision avoidance. In the simulation, it appeared that you were using some ray type simulation. Did you also use here this point cloud representation that you would get from the sensor, or was it really just a single ray distance measurement?
Yes, so it's a plan to take also the point cloud and to integrate into our simulation. So we didn't do it yet, but we will do this. Yes, it's our plan.
Okay, so this is related to some work that we also do here. So that's maybe interesting. interesting link. The other thing, basically, also since we are interested in sensors, so from your point of view, with respect to the grasping, you think that proximity perception here, really for the short distance, for the last centimeters, millimeters, will be important for the grasping, or you say, okay, it's tactile that we need and.
Yes, for sure. It's very important. It's very important to detect the collisions when we are grasping the object, because the object recognition system could be not so precise. We tested some sensors, for example, as I already presented, radar sensors, but they're not so accurate. So the distances are not so accurate. So maybe for avoiding the collision with other robot or with the environment, it's okay. But if we are talking about grasping, these sensors are not so precise right now. Maybe there are also some other sensors from other manufacturers, but what we had or what we have, they're not precise enough.
Okay, thank you.
Thank you very much. I would just close with one small question from my side, because you briefly mentioned food grasping, which might also be another application. And you also mentioned that you still didn't try to grasp real fish because of all the problems. I was thinking if for the project or in general, there is a plan also to consider some sort of force sensing, or maybe some tactile fingers of the gripper, you know, because when it comes to food, then the different consistencies, you might risk to break, you know, a tomato or whatever. So
yeah, it's true. To damage the food, first of all, and the second of all, for example, the fish are slippery, yes, so we can lose the fish during the movement, and now we can program. We programmed already this function, so we detect the position between the fingers. It's very close, it's very small, so the fish is lost. But actually, it would be nice to have also tactile feedback.
all right, thank you very much. As everybody said, it was really nice to see a lot of examples with different robots and different applications and different sensors. It was really good and complete. So thanks again. I will hand it over now to Kaspar for the introduction to our next presenter.
Yeah, thank you, Barnaba. And yeah, it gives me a great pleasure to introduce the next speaker, Thomas Pilz. And he comes from the company Pilz. It's a family business, and there with his sister, he is in the management of that company, in the third generation, I have read. And yeah, just to give a quick overview, Pilz started in 1948 and was focusing on glass blowing, so a glass blowing business. But what I really find exciting, how quickly the company then evolved from that initial business and really went with the times and established itself very quickly as a leading company in safety engineering and automation. And I had myself the pleasure also to work with Pilz. That was in the framework of an EU project. And that really shows to me how interested the company is in, you know, in further developing and also taking on board the newest trends, the newest developments, and really has the great interest in engineering. And obviously then uses that to contribute with new solutions for advanced automation in industry. So it's also very strong in contributing to Industry 4.0. And we had this short chat earlier, Thomas, and I hear that there's also interest in AI and machine learning. And I find that particularly interesting because I think many companies are very reluctant to go in this direction, especially when safety is involved. So I'm really looking forward to hearing from you, Thomas, about the newest trends at Pilz and what the future holds. So yeah, pleasure to introduce you, and over to you. The floor is yours, Thomas.
Thank you very much, Kaspar, for the kind introduction. Let's see if I'm capable of sharing my screen without too many technical errors. Can you see me?
It's coming up.
Wonderful.
Yeah, now it's there. Yep, perfect.
Now, when you read the title, it's kind of a provocation. Safety is the key for proximity, today's and future trends. Why do I call it a provocation? Because research really doesn't need safety in order to solve the problems we've just seen. When it gets transferred into industry in an industrial use, then it becomes a challenge, because a lot of things that we see in laboratories work just fine are, due to our regulation, let's take the machine directive in Europe, for example, not admissible into a shop floor of a plant. I do believe so that the topic of service robots does change this very much. I do believe that the field of intralogistics will pave the way for new sensing technology much faster than our traditional industrial applications. Some of the drivers I've listed on this screen. Another thing is, you see our nice laser scanner mounted on this AGV. Why is it there? Because you have safety regulation requiring such a device on a robot. It would navigate just fine with any of the other technologies not safety certified. But what is the advanced usage of such a laser scanner? It is through ROS modules that we develop that give the navigation information to the SLAM algorithm. And that then gives a dual use of a already needed safety sensor with the boring old safety function. It can have very exciting new deliverables to, in this example, SLAM algorithms. So you need to have a clear look at what is safety function. There you're basically handcuffed by the industrial standards, and what is any other function that a service robot or an industrial 6-arm robot needs in order to, as seen in the last example, grasp a fish, for example. And if you remember how many sensors were necessary in order to grasp a fish, to detect a fish, to differentiate a fish, if the other information of a point cloud can be evaluated by a safety unit, you have a dual usage of the sensor technology that is there. And I really loved the example of the 3 sensing technologies, the radar, the TOF, and the stereo camera, how you combine it in order to achieve your objective. And I believe, saying that in advance, this is the trend in the industry. It's not to create a safety sensor per se. It is to create a application where you can work. And that is just a little provocative statement again. Safety is about humans, not about the standards. And that's why I'm focusing on the industrial standard 10.2.18.2 that describes the application. There's a 10.2.18.1 that describes the safety functions that a robot arm has to have, that a robot controller has to have. But really, in the application part, the 10.2.18.2, we are starting to get a safe application, just like a safe fish picking robot, a safe AGV transporting parts from A to B and loading and unloading it with the onboard arm. Why do I say that? Because I just hate the word cobot. I just hate the word safe robot, because it gives a wrong perception. There is a lot of engineering needed. There is a lot of sensing needed in order to bring a, now marketing term, cobot to the market. There is always sensing involved, even in the standard. When I have speed and separation monitoring, that's our topic of today. This is where safety has been a story of failure. And then you have power and force limiting. This is where safety has been a story of success. You've seen the KUKA arm. It is equipped with safe sensors inside the arm for the power and force limiting. This, however, makes the application really, really slow. If we look at speed and separating monitoring, one of the reasons for failure in the field is the distances that you need to adhere to and the tests that you need to go through when you're a manufacturer of a safety sensor. When we developed the safety eye, which is the first safety camera on a 3D stereo algorithm base, we had 20 years of work to be improving not the safety function, but to improve the reliability of the system. Because in safety, the paradigm is when you're not sure, you shut off. When you shut off, you kill production. Now, if you look at the 4 revolutions that Kirill showed in his first slide, we were ahead of time because we didn't have the robot functionality that would allow for a collaborative, slower mode when a worker is present. We always had to shut down. We never got a balance between productivity and safety because in safety standards for sensors, you need to take the worst case scenario, not the expected scenario in a workplace. You heard about the lighting that is needed in order to detect the fish properly, in order to give the sensors a chance to identify the object. In safety, you have to have an opaque background, an opaque object, and you have to detect it to near no view. It is very interesting because you could use such a field everywhere, but you need to use it in a controlled factory environment where you have lighting requirements as a minimum for a human to be allowed to work in, where you have trained personnel and you cannot assume normal lighting conditions. That is why in safety, you always add distance. And if you want to go into a speed and separating monitoring, you need to have close distance. So this is where the challenges of safety, when transported research results into the workplace, really give you a hard time. So the next story of failure is cost. I mean, we did develop a safe skin. We tested it together with KUKA back in Augsburg. The results were equally good as the internal torque sensors. They were pose independent. But then there was the first challenge. It would heat up the arm to an extent where it wasn't good for the electronics inside of the arm. So you have to look for that environmental, just like at the fishes. If you have the gripper that can grip it, if you have the sensors, you need to make sure you have the certification, you can use it in the food industry. And everything that you have needs to be able to withstand hosing with a calcer so that they can clean it. You need to look at your mechanics so that you don't trap food that can rot and poison the food that you're working with. So what I'm trying to say is even after we've solved all those obstacles, you still have to look at the particular regulation for a certain industry in order to make things work. But to me, speed and separating monitoring is now exactly at the tipping point. We had the tipping point for power and force limiting much earlier, and I believe with all the research being done right now, we're at the tipping point for speed and separating monitoring so that you can get acceptable performance for a machine, for a mechatronic system. That's an old word, I like it. Others say cyber-physical system, modern world for exactly the same thing, but that's what I believe will free us up for service robot type devices. For that, you still need laser scanners, You still need safety radar sensors that are on the market. You would need capacitive robot skins. You would need safety cameras. You would need all the results that the researchers are currently working on in this field in order to come up with solutions that allow this little service robot to drive through a warehouse which is operated by humans. And this is the very interesting field. I do believe that the proximity sensing allows for low-cost warehousing compared to the high-cost warehousing that Amazon, for example, uses right now. Amazon has Amazon Robotics. They have a very well thought of system with very high need for computation power in order to select things. And that to me is very expensive, that only a company like Amazon can afford. But there are so many small warehouses out there that a human with human information does the picking and bringing to a counter. And if I had a robot that can drive next to some of the human people using barcodes or whatever is needed for the human to find the part, we would have a much less cost-intensive solution where people would dare to use it because they can interact via gesture, via voice, and they could be protected by proximity sensing solutions that makes you feel comfortable next to a machine, because that to me is power and force limiting. Why are large robots not really accepted for power and force limiting? Because humans usually on a psychological scale feel uncomfortable with a large machine that can move really, really, really fast. So that's why method 4 only gets you half the way. What is the future? In my opinion, we at Pilz, we focus at the moment on radar technology. We do focus on the sensor fusion, and we do hope that through the failures in safety that we have made so far, in the future, we can be participating when the success with safety does start, because research, you only advance with failure. You know it works in theory, failure commercially in industry. So you change the parameters and you move on. And this is basically what Pilz is all about. We try things out, we hope to fail fast, and then with this get the information so that we can move on. A very interesting question for companies like Pilz is, how can we collaborate with machine builders like a KUKA when there is the availability of embedded sensor technology? What is the shape? What is the need for a robot manufacturer in the future for sensors? Is it what you can see on this picture, something with a housing, or is it just a German word Halbfabrikat, HBF, I'm sorry for having to switch to German, semi-finished product, I think is the right word, or is it a different word, embedded system with a safety pre-certification that a company like KUKA could use in their system to adapt it? Because that's one thing that Pilz has learned over its history. If you're unable to change as an organization, you will be eliminated from the market. So we do hope that with the modules that we can provide, we can stay in the exciting field of robotics with our core competence, which is safety sensing, with outputs of additional information to application needs. And with that, I'm hoping that there are some questions that we can talk about, because I did reach my last slide. Thank you so much for your attention.
Yeah, thank you very much, Thomas. Fantastic overview. I actually have some questions, but there were others with their hands up more quickly than me. So let's start with Stefan with his first question.
Oh, thank you. Thank you very much. That was really quick then. Thank you for this very interesting talk. So yeah, I really like this perspective on the combination of safety, costs, and you know, also this new kind of newer aspect of speed monitoring. And I was wondering, so suppose imagining that we have a solution that is technically functional, so it's providing the functionality that is desired, is we can certify it, and it has some increase in productivity. How do you see the balance between the costs? Because you also mentioned that for the certification process is at the solution level. So it's not like I can buy a robot arm and say, call it safe. I have to look at the solution. And so yeah, is this value proposition going to be attractive or not in the near future? So that...
This is a very, very difficult answer. I can only give it as an example with our spatial resolution tactile skin, which is textile based. There, we were unable to be competitive when it comes to a laser scanner by guarding a flooring, because the square meter was more expensive when you had to put 6 mats together, and you can easily do that at a much lower price with a laser scanner. So therefore, it was not so much a success. Then putting it around a kinematic where you have electronics inside, you need to make sure that you don't overheat the electronics inside. So it wasn't much of a success either. That's what we've learned. Now, will it get less expensive when you need smaller spaces? Would it be a good solution for a gripper finger? Maybe. And then you have to end develop it. And then only then you can see if the value that the customer gets is there so that he is willing to pay the price for it. So maybe there is a huge value because nobody wants to sort fishes very much. For a 2,000 euro gripper, match that with a 10,000 euro arm, you're at 12,000 euro. But if you then have the algorithms, you are at a 50,000 euro price tag as a minimum when you're inexpensive. Now the question is this a value in Europe? Maybe. Is this a value in Thailand or in Vietnam or even in China? Maybe not. So it all depends there.
Yeah, thank you. So, but I was this is already answers a part of my question, or the question I have is also about the cost of certification. So, do you sometimes, if you have a new technology you want to certify, it takes a long time for the provider of this technology to certify. So, is this also a kind of stopping stone for this developments, so that people say, oh no, I won't even risk this development because it takes so much time and money?
The challenge there that it costs you time and that you have to do documentation in a certain way. And that is something that researchers really don't like so much. So it's a necessary evil, and it's a quite significant cost factor. And then last but not least, you have a third party that is authorized to not accept what you think is good. And that sometimes is very hard to swallow, because you have to defend your safety concept, you have to defend everything that you've done, and then there's somebody coming and says, nah, I don't think so. And then you're really in a trouble because you need to do everything again so that you meet this evaluator's concerns.
Okay, great. Thank you very much.
Yep, thank you. Over to Yitao.
Yeah, thank you, Thomas, for a nice presentation. I was always wondering about these safety stop buttons and safety hold buttons in the industry. So, I mean, the most intuitive way, if something fails, you just stop everything, right? And you also said that if you're unsure, just stop the motion or shut the system off. But do you think that is this always the case? So is shutting off or halting the system always a good solution to ensure safety?
I sound like an attorney now. It depends. It depends on your risk assessment. If you create a bigger hazard by abrupt stopping, then you should have a stopping ramp to come to a secure stop. If you're in the air with a drone, you better not stop your rotors if one rotor has a problem and you try to land the thing. So in industrial automation, the mechanical hazard was usually something in motion. And therefore, in the field of industrial automation, the stop is considered the safe state.
Great, thank you.
Yep, thank you. And Kirill, you have a question too.
Yes, thank you, Thomas, for the nice presentation. So my question is regarding detecting humans with the different sensors. I know there are different regulations for this regarding data privacy and so on. So what do you think about this? How it's possible that we can detect humans and production sites and so on?
Kirill, it is possible to detect humans with radar technology. That's why we are focusing on industrializing our research results there. We already have a system which only detects objects, and the next generation will detect humans. I do, however, have now a challenge in front of me, and that is the change from the machine directive into machine regulation, giving already requirements for artificial intelligence when used in safety applications. And because that's still in the feedback stage to the European Union, I don't know what really will be in the regulation. The challenge that I see there is we wanted to use learning algorithms to improve the detection. Now there is a requirement that in the text of the machine regulation, you have to have a third party that assesses it because it's a high risk, and you have to prove the learning results. And that, to me, at the moment, stops everything that I want to do with regards of safety functionality, because I'm unaware on how to prove the learning results of a learning system in the field. This is something that needs research, that's something that needs work. And therefore, I'm at the moment a little bit frustrated because we are on a good path, especially with academia through the European research programs. And now we get this regulation in front of us, and that may stop us in Europe from taking advantage of what's acceptable in Asia. And that at the moment, I'm really concerned that we have to be stalling in the field of safety. But my way out is then I'll just make it a navigation function, and I create with conventional technology a safety function around it and happily live ever after. But I would love to be able to really lose the traditional safety sensors and have the sensors needed for the application provide the data to a safety control unit that then controls the reaction in regards of hazard avoidance. But we know more by the end of 2021 when it's released where we stand, and then we take another hit at it. But for the moment, I can say without artificial intelligence, we can separate a human from an object.
Okay, thank you.
Thank you. I'm also looking forward to what's happening on the AI and machine learning front in safety. But Matteo and then Björn have also more questions.
Yeah, actually, my question just got answered because I was also really interested in relation with artificial intelligence and safety. But yeah, you just, so thank you again for the presentation, but you just answered basically everything I wanted to ask. So Barnaba texted me that he also has a question, but he cannot find a button to raise the hand, just that you know. So also Barnaba has a question.
Wait,
Okay.
it's not that I cannot find it. I know where it should be, but it's not there. I think I have a holded Zoom version.
Okay, shall we move to Björn and then to
Yes,
Barnaba?
please, just so that you know. Thank you.
No worries.
I mean, first of all, thank you for this beautiful crafted overview regarding these issues, what you talked about. For me, the question would be also, if we look at, so a typical SME, they know their process, and now they want to get human in the process, and suddenly they have to tackle the issue of safety. And then there's the safety assessment, and suddenly there are no experts. So, and what is your do you think in the near future or in the midterm future, can we get rid of the experts to certify a system? Or how far we are away?
Well, I do believe that you will never get rid of a human for the final thumbs up of a system. But like it is in the automotive autonomous driving, you will have assist systems so that the person who finally has to take the responsibility in terms of the law is being assisted in a way that you don't need to find people like me that have been in the standards environment and have some sort of education on how to interpret and how to conduct a risk assessment. So I think in the midterm, we will get much better tools to assist engineers to have a risk assessment done while they are engineering. Because when you do an engineering project, you do a risk assessment, you just don't know it. Because you assess what you want to do, and when you say, this is what I want to do, this is the expected pose, this is what is happening, then if you would only be able to fill out the Excel sheet at the same time, you would have everything you need. Let's take the grasping function and selecting the grasp where you don't lose the object. If it's a sharp and pointy element, this already could be seen as a safety function, because you shall not drop in a service robot environment a heavy, sharp and pointy metal piece on the foot of the worker standing next to you. If you know that you will not drop it, it is a safety function. Just don't tell anybody from the safety industry this, because then they're going to ask, by which PLD performance level will you make no mistake by taking out one pose where you possibly with this 0.9 probability will drop the part anyways. So this is the name of the game. You have to come up with a performance level. You need to calculate BC, BC, BD, 10. Sorry, today me and numbers. Calculation with a Markov chains, and that's where you're hindering your effort. So to me, it's great because I know that I'm not going to drop because it has been simulated. And this is a function. This is not a safety function, because the moment it's a safety function, you need to say by which probability will you make a mistake.
Yeah, thank you.
Thank you. Okay, then over to Barnaba.
Yes, thank you. Now, more than a question, I have an occasion for some knowledge sharing, because it's quite a nice coincidence that my latest research is exactly on these topics. So in this slide here, you have the detect humans and distinguish between humans and moving objects like another AGV. and with the speed and separation monitoring out of the ISO 15066. So it's interesting to see that this is actually something that is being done. So I worked on an algorithm, and yeah, now at the IROS, actually, I will present a paper showing how to distinguish with a radar sensors between humans, and we had a mobile manipulator robot in-house, and then how to assess this with the speed and separation monitoring. So before, in one of your previous slides, you showed the standard configuration where you have these 3 detection zones, and according to the distance, you either go at full speed with the robot, half speed, or you just stop, right? And so the idea that we had was, why does this need to be in steps? You could control continuously the speed of the robot, right? Basing yes on the distance, because you have this formula where you consider the distance of the human, the velocity of the human, but the standard formula in the ISO says you always look for the worst case, right? And with the radar, the super nice thing you have is you directly measure velocity. So you can include the actual information of the velocity of the human directly into the formula, and therefore you can so the whole goal was to increase the productivity. So we had some comparison. It's exactly what you showed. It's really a nice coincidence. Increase the productivity while still maintaining the level required by the speed and separation monitoring, right? But changing the robot speed continuously and accordingly to how the human was moving and how fast and in which direction, and so on and so forth. And if the target was a human or was another AGV. Because this is also a good, a very nice thing that I like that you highlighted, because if you have just a robot moving, and the robot is maybe going to another robot, obviously this is way less safety critical, right? Because with safety, we deal with humans and not with machines. So yeah, that was actually extremely nice to see. Maybe one question there, would it be, okay, but let's say now you have your system that does this, and I have my system, or at least that my research that does this. When we want to put it into the production and we have to get a safety approval by someone, is there a way that we should say this is safer than this and this and this, or either it is safe or it is not? So what's the current regulation in this?
I hope there will never be a competition. This is safer than the other solution. It should be, it is safe, and the technology is implemented in a proper way. The challenge that you have, the challenge that we have, the challenge that Kirill has is you will be asked by the radar standard to pass the worst case detection test criteria, which are normally, when it's a safety sensor in itself, in chapter 4. And the problem is then the distance. How the yellow part here is where you certainly have an uncertainty whether you have really detected a human or whether you have really detected a robot. Then there is the question, what happens if your sensor loses the human? Do I then have to stop? And that's where everything that works fine in a normal environment, where your algorithms are equally good, if not better than what we have, are being put to the challenge by a BG in Germany, for example. And then they say, yes, you're working fine, but it's not good enough in terms of safety. And that's when the frustration really starts. We had it for 20 years with our safety eye. We had people with a pencil putting it in and says, it's detected. And I said, yeah, but I can't say that it's detected with the required probability. And the probability of a failure is that I can't say that it is finger safe. And then they asked us to have distances. Then all of a sudden you have a floor that jumps into the sensing field, even so the floor doesn't jump, but because of the stereo algorithms, floors do jump, and then you have to put it up. So the robot standard helped because of the regulation, how far a safety fence and a light curtain can be mounted above the ground to prevent somebody from crawling under it. And all those things make it very frustrating when you implement a sensor per se into an unknown application, because that's the problem of a sensor manufacturer. The application is unknown. I think we would have a much higher probability of success if we would work together with Kirill and say, this is the scenario. We have the controller, we have the application in mind, and with those sensor algorithms in this particular application, we can have a safe solution. What is the economical problem there? You would have to reassess each application at a time. And that again is the question from Björn. Where the hell do I find all those experts that are going to actually give me the application specific green light to use it? So these really are the stopping stones, or I would say the delay. This is the delay part when you talk to safety about it. We would be much further with human-robot collaboration if there wouldn't be the worst case scenario requirement in industry. What is the benefit? The benefit is that we have very, very few fatalities in robotics. We have very, very few high injuries, and that is the human part in it. Nobody wants to lose somebody they love and that they know. When you don't know the people, statistics give you different answers.
Yes, thank you.
Yeah, thank you. I hope it's okay if I add one more question. So I would like to come back to the safe skin that you spoke about, and if I understand correctly, that was fairly successful. However, there were overheating problems, but I suppose that is a technical challenge that could be overcome at some point. So I'm wondering, maybe I didn't really understand how the skin works. I assume it was a tactile skin. So if you were to extend that into a proximity skin, so I'm imagining a skin that is covering a whole robot arm and has the ability to look sideways at every point, would that be useful?
You need to ask Kirill more than me. I think it's very useful, and I love textiles. And I loved the possibility that it can scratch, but when you stretch it, you have a change in the capacitive sensing. I know that I can have an aura at least that high with it. So there is a lot of potential at the moment. It's a technology that we have where we are working with and see how can it be put to use. But really, it's an overload of sensors. Now try to convince the colleagues from Kirill that have all the torque sensors in the robot that makes the robot really expensive, why they should add another layer on it. And these are all the questions. As you may know, we even developed our own arm in order to have something to work with and see how it works. Now our mechanical partner decided not to continue, so I have no arm anymore. So that's another drawback, but at least I had my research objective done. I know now what interaction do I need, what reaction times do I need between the sensors and the arms. And I also know how powerful ROS is as an interface. To me, still the ROS modules are a disruptive challenge for established robot manufacturers, because you can do a lot of things as long as you're able to have reliable mechatronic arm elements. Because you cannot underestimate the value of a high precision arm as the arms that KUKA actually offer. And it's a lot of work to make this arm with Überschleifen work very smoothly. So that must not be misundervaluated.
Yeah, I'm happy to extend the question to Kirill. When I saw you mention tactile sensing in your last slide. So if you had this kind of proximity sensing skin all around your your grasping fingers or even robot arms. Would that be interesting, useful from your perspective?
Yes, sure, it's interesting. But as Thomas said, it's really could be a problem for mechanical design and from price point of view.
So, sorry, could you just repeat the last bit? Sorry, it didn't come through.
So it would be nice, but the problem could be mechanical design and also, as Thomas said, mechanical design and price. So for sure, it will be not so easy, but it is interesting for sure, and it can help.
Thank you very much. Yep. Thanks from my side to both speakers. I learned a lot, and yeah, thanks for giving me these fantastic overviews. And I pass over to Yitao possibly, or Christian.
Just to conclude everything, or just final words, we have our next sessions on 26th August. And there are quite a lot of sessions on that day, I think four sessions. So it will be like a full day workshops, or similar to a full day workshop where we have all the rest of the speakers, including the PhD forum. So if you are interested, you can, or please join if you're interested. And I think there will be many interesting talks and also discussions in the PhD forum. Where we can see latest research results and on our ongoing research. So with that, I'll thank everyone for attending today's session, and hope to see you next time.
Yep. Thank you very much.
Thank you very much.
Thank you. Also, thank you from my side to the speakers, to the interesting talks, and also to the interesting discussion we had. Thank you very much. And we see us latest at the 27th of September or next week.
Perfect. Take good care, everybody.
Take care.
Thanks a lot.
Bye.
By the way, Kaspar, now that I saw your picture with a different hair, now I remember. You lost hair at me. And it was my Spaniards that were in this project. And that was basically a rogue project where nobody in Germany knew about it until we had that event. I see. Even in a small company like mine, I don't control everything, and I don't ever want to. If I'm not giving my people the freedom to do things, we're losing out.
Yeah, no worries. Good to meet you again.
Good to meet you again as well.
See you later. Bye, everyone.
Bye.
Thanks,
See you.
everybody.
Bye. Take care.